Okay, so we're going to expand on some of the stuff that we did just a moment ago, and this is a useful thing. Every so often they've asked questions like this before on the AP exam. So we're going to finish up looking at some of the calculus applications for kinematics. I went through and did a somewhat hand-wavy, but for the most part everything that you would need to do, derivation for our kinematic equations that we use on a regular basis. And I said that we were relying on the following relationships. The acceleration is defined to be the time derivative of our velocity. Our velocity is also defined to be the time derivative of our position, both of which being functions of time. Now the first thing that I had you all do, well, that I did when we went through this, was we said that we assumed that the acceleration was equal to a constant. And that's how we got the equations that are featured on the equation sheet that I give you all. They're also, at least the 3 out of those 5, are the equations that are featured on the AP equation sheet, so the AP exams equation sheet. There have been times where they bring up the possibility of equations that are not for a constant acceleration. And so in this case, we're not going to assume that the acceleration is constant. We're going to assume instead that it is equal to 4 times t. Where, I guess, 4 would have units of meters per second cubed, because the acceleration would be in meters per second squared, so then we multiply it by a time, usually in seconds, and we would need that to have appropriate units. Now, the 4 in this case, if we were to take the derivative of this, small side note, if we took dA dt, that would give us something that we talked briefly about in class, which is called the jerk. Now, that is something that describes the rate of change of the acceleration, how quickly you are changing your acceleration. So in this case, the jerk, we take the derivative of this with respect to t, and we'd end up with 4. It would be 4 meters per second cubed. Now, that's not a thing that we're actually going to be working with in this, but go ahead and mention it since we're in passing. This is a changing acceleration. It would have a time derivative, which would give us the jerk. I don't actually know what the variable for that is. I honestly haven't used it that much. Most of the stuff that we encounter in the real world, at least at the level that we're working with in physics, we mostly assume that it has a constant acceleration or pretty much constant acceleration. And when we get to forces, we'll see why that is. All right, enough chatter about getting things in place. Let's see where we're going with this. We're going to assume that my acceleration is a function of time and that it is indeed equal to 4t. And you could replace this with any function of time. You could even have 4t squared plus 2t or something like that. And you would just go through the same steps we're doing. The important thing is we're using an acceleration that is a function of time and is not a constant. All right, so here we go. We're going to use this first relationship. Our acceleration is equal to dv dt. I'm going to drop the vector signs even though we do know that this is a vector. I'm going to be a little lazy. So here we go. My acceleration is actually equal to 4t with some units, and that'll be equal to dv dt. This is my acceleration in this case. So I'm going to multiply both sides by dt, or at least that's how you can imagine it. We're doing separation of variables, possibly misspelled. Then we end up with dv equals 4t dt. Now remember, this is an infinitely small piece of our velocity over an infinitely small piece of time is a good way of thinking about it, and that gives us our rate of change, which this is our acceleration. So this is a relationship between our velocity as a function of time and time, the thing it's a function of. When I bring this back out, I go from an infinitely small piece to the finite increment. Then we go from our initial velocity to our final velocity, and our final velocity could also be marked that it's vt. It'll be the velocity at time t, but we'll just do initial to final to start off. But when I expand this side, take it from infinitely small and make it back to a finite value, I must do the same thing over here, and we're going to go from time equals 0 to time t. Now technically, once again, I feel compelled to mention it, in the proper rules of mathematics, it is improper for me to have a limit of integration be the same variable that I'm integrating with. Now, I could do t star or t prime or something like that. I'm not going to bother with that, but I do feel compelled to mention it because there are probably math teachers out there somewhere putting a hex on me or something, I assume. All right, so this evaluates to v, evaluated from v naught to v final, and then we're going to do the integral of this. Take a look at the other video if you're still new to integration on how we would actually go through that. We do not need a plus c because we have a definite integral. We have limits of integration, and so we're actually going to go through and we're going to evaluate this. Well, this would go to t squared, so let's see. We would have 4 divided by 2 t squared. There's the 1/2. That looks great. And we're going to evaluate that from 0 to t. Great. All right, looking good. So I'm going to evaluate this. I end up with v final minus v initial equals 4 divided by 2. That's going to be 2 t squared, putting in t, minus, well, 0. So anyway, we end up with following. V final minus v initial equals 2t squared. So we would end up with the following equation. My first equation, the one that comes first on our equation sheet that I gave you, if it weren't constant acceleration and instead our acceleration were equal to 4t, not a constant, this would be what our first equation would look like. I add the initial velocity over here plus 2t squared. That's what we would end up with. Now you'll notice that we've got something a little bit different here. I wouldn't really put this in terms of the acceleration. We do have an acceleration in here, but it's combined in this. And so this is our first kinematic equation that we would have for it. More to the point, I wouldn't really call this a kinematic equation because it doesn't have the acceleration explicitly listed. But what this is velocity as a function of time. Here's our initial velocity plus 2 times t squared. Now, we could go through and we could try and find what the acceleration is, but we'll see that it's a function of something else. Again, don't try and wrap your head around this too much. The important thing is we've now found the velocity as a function of time, which is partly what that very first equation is. This is also why we don't just have a set grouping of equations for if the acceleration is not constant. If the acceleration is constant, then we can leave a in there and you would just put in whatever value it is. This equation will change if a is not 4t, if it were 6t instead, then we would end up with a different value here. We'd have 6 divided by 2, and we'd end up with v naught plus 3t squared. That can get a little bit trickier. We could probably turn this into a kinematic equation where we have a constant times t and have kind of a general form for it, but this is how you would end up doing it. Okay, well, this is our velocity as a function of time. Let's take it to the next step. Let's go ahead and find that we know our velocity as a function of time will be equal to the derivative, the time derivative, I should say, of our position as a function of time. Okay, well, now we know that this is my velocity as a function of time, or at least that's what we found. Here's my velocity as a function of time. I put in t and my initial velocity, and that would be vt. It will be equal to dx dt. We do separation of variables on this, dt. Now remember, it's the whole thing. We end up with the following. I'm going to go ahead, well, yeah, let's do it this way. dx equals v naught dt plus 2t squared dt. This is me distributing the dt, and I swapped the sides here. Now we're going to integrate. We're going to go from x naught, our initial position, to our final position at some time t. I could, instead of marking this as final x, I could make it x of t, even though, yeah. Then I need to integrate this side from 0 to t. Time equals 0. Our initial time is going to be 0, all the way up to whatever time we want, which is t. I can then do, well, this is going to become x evaluated from x naught to x final equals, we've got the integral from 0 to t of v naught dt plus 2t, integral 0 to t of 2t squared dt. I like writing it out like that so I can see it a little bit more clearly. A few things. 1, initial velocity is a constant. It can come out. 2 is also a constant. It can come out. I'm going to evaluate this. That'll be x final minus x initial equals, let's see, v naught times t plus 2 times 1/3 t cubed. And then the lower limit is 0, a whole bunch of zeros, so that actually kind of disappears. So we would end up with this. Final thing that I'll have is, remember this is final minus initial. We can describe that as delta x equals v naught times time plus 2/3 t cubed. Here's one of the other kinematic equations. Now remember, this is not a general solution. This is the kinematic equation, the position as a function of time, if your acceleration happens to be equal to 4t. Now you can go about doing this with an indefinite integral, and you would have plus c's, but you would need additional information where then you would fit it to boundary conditions. In this case, I'm kind of doing the general stuff where we go from our initial to our final, from 0 to t, and then we also went in the velocity from initial to final effectively. And since our final is determined by wherever t is, we can also kind of switch that out with, that becomes our velocity as a function of time. All right? Here's making your own kinematic equations, if you will, if you have a non-constant acceleration. Now, to find out what the acceleration looks like, you would need to look at the problem and look at the forces involved. That's where we're going next. We're going to start studying forces and see they're the things that cause accelerations, and we can probably predict, given enough information, what the accelerations would